All right, so from this original differential equation with initial values, we took the Laplace transform on both sides and simplified and made some substitutions and isolated Laplace of y and ended up with, we don't know what y is, but we know its Laplace transform is this function, 2s plus 3 over s squared plus 2s plus 5. So we want to split that up into some useful format. And as you mentioned, we've got the functions that look kind of like that. We know from the Laplace table that Laplace transform of specifically e to the a t times sine of bt is going to look like b over s minus a squared plus b squared. And likewise, Laplace transform of e to the at times cosine of bt is going to look like s minus a over s minus a squared plus b squared. And an important thing to note here is that these are almost exactly like the Laplace transforms of just sine of bt on its own and just cosine bt on its own, except with every s replaced with s minus a. In fact, in general, if you multiply the function of t by e to the at, that has the effect of changing the Laplace transform by replacing every s with s minus a. So let's see if we can make this Laplace transform look like some combination of these. And we should kind of expect that anyway. If the characteristic quadratic leads to complex roots, we should expect some combination of sine and cosine multiplied by exponential functions. And you mentioned completing the square. How would we complete the square on this? If we want to write it as something squared plus something.
I'm not sure, but we could take s squared plus 2s and try to complete a square with that.
Yeah.
And then subtract it with 5.
Right, that's what I would usually do. Ignore the plus whatever and just figure out what plus a constant would make this a perfect square. For example, if you have, in general, if you have s squared, or let's say you start from a perfect square. Let's say you multiply s plus, let's say s plus p, and you multiply it by itself. What would you get?
S squared plus 2p plus p squared.
Yeah. Which means that the coefficient on s, half of that has to be what we're adding here. Same idea here. This coefficient on s, we take half of that and put that here. That way, if we were to multiply this out, s plus 1 squared would become s squared plus 2s plus what?
1.
Yeah, plus 1. But we don't have plus 1 here, we have plus 5. So what more do we need to make that actually work out?
Plus 4, but since it's b squared, would we do 2 squared?
Yeah, that 4 could be thought of as 2 squared. So that suggests that what we want to split this up into, since the denominator can't really be changed, we can change how we write it, but we're not changing the value of the denominator. We want to write this as s plus 1 squared plus 2 squared. So let me make that replacement. We know the denominator can be rewritten as s plus 1 squared plus 2 squared. And now ideally we want to split that into b, that is 2 over that whole thing, and s minus a, in other words, s plus 1 over that whole thing. So let's identify a and b now that we've got it. We know a is -1 because a is supposed to be what's being subtracted from s. And b, it looks like, is 2. So to figure out how all of that plays into this, let's actually try splitting this up. We want to split it into something with an s, possibly, and also a constant, and also something else with just a constant. And what we have is something s plus a constant. So one way to do this would be to, first of all, we have 2s, but we want this to be just 1s. So we might want to start by factoring out that 2. If we factor out that 2, then we're left with 1s plus 1.5. Or let's just write that as 3/2. But that doesn't quite match. What do we want the numerator to be? In order to match exactly s minus a, what do we want the numerator to be here?
The 3/2 to be minus -1.
Yeah, we want this to be s minus -1. In other words, s plus 1. The idea is that the numerator here in the e to the at cosine bt should match this term in this squared in the denominator. And they don't match. We've got s plus 1.5 versus s plus 1. But what we can do is we can split that up. We can write this as s plus 1 plus how much extra?
(1/2).
Right. If we split that 3/2 into 1 plus 1/2, then that way this term matches this, and then we've also got plus a constant, which is going to look like this constant here, the b. So let's go ahead and split that. We can now split this into 2 times s plus 1 over the whole thing plus 1/2 over the whole thing. So this is now perfect. We have s plus 1 over s plus 1 squared plus 2 squared. That precisely matches this format. Does this one precisely match this format?
No.
Not quite. What does the numerator need to be in order for this to work?
2.
Yeah, we want the numerator to be 2. However, we can fix that with multiplication, because we could certainly have an extra times a constant on the outside and pull that out of the Laplace transform at the end. So let's make a modification here. What multiplier would turn 1/2 into the 2 that we want?
4. But
Yeah.
do we also need to consider the 2 outside?
We do, but we can always put that in at the very end. Since it's just a constant multiplier, we don't have to worry about it yet. But for now, I would just look at it in terms of this numerator needs to turn into a 2, so let's multiply by 4. But since we multiplied by 4, we also need to balance that out by multiplying by 1/4. Of course, we can write that outside the fraction itself. Within the fraction, we now have 2 over something squared plus 2 squared. So that now precisely matches this format. Any questions on that so far?
No.
So let's see what that becomes. And at this point, yeah, we may as well distribute the 2 to both terms. But I'm going to leave those times 2's outside the fractions because we now have these fractions looking exactly like we want them. We've got 2 times s plus 1 over this whole thing plus, and then we've got 2 times, and I'm going to combine this 2 with this 1/4 to get 1/2. And then the fraction itself, we got the 1/2 times 4 becomes the 2, which is exactly what we need, divided by the entire denominator. So now these are exactly in the right format. We've got 2 times precisely the Laplace transform of e to the at cosine bt, plus 1/2 times precisely the right format for e to the at sine of bt. Any questions on that process so far? And now we can actually take the inverse Laplace transform. Formally, we're taking the inverse Laplace transform on both sides of the equation. On the left side, that just turns into y. So looking at each term individually, we've got 2 times something that turns into e to the at cosine bt when we take the inverse Laplace transform. It's just that we now know a is -1 and b is 2. So we can write that out. We've got 2 times exactly this, e to the at, but we now know a is -1. And we also know b is 2, plus 1/2 times this, which is exactly this format. So it should turn into e to the at sine of bt, where again, a is -1 and b is 2. So this should be the specific solution of that initial value problem. Any questions on that so far?
No.
And this is generally the sort of procedure that this is going to involve. Once you apply the Laplace transform and isolate Laplace of y equals some function of s, your general goal is going to be to algebraically manipulate this entire side of the equation to rearrange things, maybe split things up, and fill in whatever extra coefficients are needed to make this look like individual pieces from the Laplace table. As long as you can make each individual piece look like stuff from the right side of the Laplace table, then you can just invert the transform directly. Any other questions on that?
No.
Or any other examples you'd like to work on?
Could we try D?
Yeah, let me pull that one up. So this one's got a 4th derivative. That changes things. So 4th derivative of y minus 4y equals 0. And then since it's a 4th order equation, we've got 3 pieces of information for the initial values. It looks like y of 0 is 1, y prime of 0 is 0, y double prime of 0 is -2, and y triple prime of 0 is also 0. So those are the initial conditions. So as before, we're going to start by taking the Laplace transform of both sides. And again, because Laplace transform is linear, we can split this up. Laplace of y quadruple prime minus 4 times Laplace of y itself. And then Laplace of 0 is still just 0. So Laplace of y is just big Y, the function of s. Any thoughts on how we could deal with Laplace of the 4th derivative of y?
Yeah. Would it be s for big Y minus s cubed y naught minus s squared y naught prime minus s double? A 2nd derivative of y naught minus y to the 3rd derivative.
Right. Going to follow the exact same pattern. We just expand that out to a quartic in this case, so 4th degree polynomial in S. And then of course we also have minus 4 times Laplace of y, which will just be big Y. So that general idea of formulas for Laplace of derivatives extends to as high a derivative as you want. which makes Laplace transforms really useful for solving any order of differential equation as long as they're linear, and I think they have to have constant coefficients also. But this tends to work really well for even if it has a non-homogeneity, because you would just take the Laplace transform of whatever that non-homogeneity is. So let's group these terms together again. Actually, before we group the terms together, let's fill in the initial conditions, because I think that is going to make a lot of this drop out in useful ways. We know, for instance, that y0 is 1. Y0 prime is 0. Y0 triple prime is also 0. And Y0 double prime is -2. So that gives us y times, and I'm going to combine those two y terms together. So we've got s to the 4th minus 4. And then it looks like we also have minus s cubed plus 2s, and I think that's it.
Yeah.
And as before, we may as well move these to the other side. Plus s cubed minus 2s. Any questions on that so far?
No.
And we do have a 4th degree polynomial here, which may make things trickier. However, it could be written as a difference of squares, right? Because we have, you can think of this as s squared squared minus 2 squared.
Mm-hmm.
How would you factor that?
S squared minus 2 plus, or S squared plus 2.
Right. So that factors nicely. And then this itself can also be factored, not necessarily with whole numbers in this case, but this could be thought of as s squared minus square root of 2 squared. So how would this itself factor?
S plus 0.5? No, the square root of 2.
Yeah. Because that way, square root of 2 times negative square root of 2 becomes just -2. And then plus root 2s and minus root 2s cancel out. So you can use that idea of factoring a difference of squares even if the second number isn't truly a perfect square, because every number has a square root, at least every positive number. S squared plus 2, you could factor it as s plus I root 2 times s minus I root 2. But we want to keep everything in terms of real numbers for now. So I would just leave this as if it were an irreducible quadratic, because in terms of real numbers, it is irreducible. So let's write that out. The left side of the equation factors into y times s plus root 2 times s minus root 2 times s squared plus 2. Does this factor at all?
If you take out the s.
Yeah, we could factor out s and get s times s squared minus 2. Wait a minute, we've got an s squared minus 2 on this side as well if we don't split that up.
Oh.
What does that mean?
Then it can just become 1.
Yeah, looks like those are going to cancel out. We can just divide both sides by s squared minus 2. And that simplifies things considerably. That's a lot less that we're going to have to worry about when we split this up into partial fractions.
Yeah.
So, of course, we're going to want to divide by this. So we just get s over s squared plus 2. So that looks much easier to deal with. Any questions on that so far?
No.
So that big Y is, of course, Laplace of little y. And then we want to undo the Laplace transform. However, we might not even need to split this up. Do you see something of this exact format on the Laplace table already?
Yeah, cosine.
Yeah, Laplace of cosine of t, or cosine of bt, is just s over s squared plus b squared. And that fits this precisely as long as b is what value?
Square root 2.
Yeah. So that means when we take the inverse Laplace transform on both sides, we get y equals cosine of bt, where b is square root of 2. So just cosine of square root of 2t. In this case, we don't even need to split out a coefficient or anything like that because it's already 1s, which is exactly what it needs to be. Any other questions on that?
No.
And it looks to me like these initial conditions were specifically chosen to make that work out. Because if these had not been exactly what they were, then we wouldn't have had this nice, neat s cubed minus 2s that would cause the s squared minus 2 to cancel out. So if these had been any different initial conditions, the s squared minus 2's wouldn't cancel out so nicely, and we would need to split that up into partial fractions, which I'm guessing would probably lead to a sine term and also a cosine term, and maybe even some exponential terms as well. But in this case, the fact that they cancel out makes it a lot easier. Any other questions on that?
No.
Or anything else you'd like to work on?
Well, I did have a question when you were saying like this is only for linear equations. So if it was y prime minus 4y, would that be nonlinear? And we can't use that?
Wait, y prime minus, what was it?
Like y prime minus 4y squared or something?
Yeah, that would make it nonlinear, which would make the, I don't think Laplace, I don't know. I don't know of a way to apply Laplace transforms to that. There may be a way. I think there's something towards the end of chapter 6 called the convolution integral that I haven't actually seen show up in 22B before, but I think it's a way to deal with a function times a function inside a Laplace transform. I haven't tried it out yet, but I think it might be able to deal with that. But typically, I think you'd only be applying Laplace transforms to linear differential equations anyway.
What if, like, for this problem, instead of minus 4y, it was minus 4ty? How would that change?
I think that would also need a convolution integral because t is not a constant, so that couldn't be pulled out.
Oh,
Be a Laplace transform. Let me take a quick look for that because I think the convolution integral can deal with that, but I've never actually tried it out. Actually, if it's times t specifically, like if you have just a times t, apparently that just corresponds to taking a derivative, no, a negative derivative of the function itself. Yeah, according to the Laplace table in the book, there's a shortcut you can use for that if the multiplier is specifically just t. So like if you had something like, I think it was the Bernoulli differential equation, or was it Euler, I forget. But if you had something like t squared y double prime plus, or at squared y double prime plus bt y prime plus c y double, or y equals g of t. So if your coefficients are just powers of t, there is apparently a substitution you can use for that. According to the Laplace table in the textbook, and I think proving this is one of the exercises in section 6.2. If you take the Laplace transform of some function of t, you get some function of s. But if you apply Laplace transform to t times f of t, apparently the result of that times t is to take the derivative of this function of s. So you get big F prime of s, and also a negative sign. And then if you multiply by t again, you get an extra negative and an extra derivative. So Laplace of t squared is going to become positive f double prime of s. And so on. So eventually you get, I think that works, negative. So generally I think Laplace transform of t to the n times f of t should end up being this alternating plus minus. So that'll be negative 1 to the n times the nth derivative of the big F function, big F of s. Any questions on that so far?
So these are only if you're multiplying by t.
Yeah, if it's specifically a times t, then that should work. Also, it seems like if you're specifically multiplying by an exponential function, like the e to the at times sine of t we were seeing earlier, there's also a general rule for that. That if you have Laplace transform of some function of t results in some function of s. But if you multiply that function of t by e to the at, then I think that just results in replacing s with s minus a. Let me check that. Yeah, that should work. And this is basically the same idea as when we had e to the at sine of t bt or e to the at cosine bt. It looked the same as it was for just sine alone or just cosine alone, but with every s replaced by s minus a. Same idea here. If you've got some function of t and its Laplace transform is a function of s, multiplying the function of t by e to the at is effectively the same as replacing s with s minus a everywhere it shows up in the Laplace transform itself. So you can use that as a shortcut anytime you've got a function multiplied by e to the at. Or alternatively, in reverse, if you have some Laplace transform that looks almost recognizable, except instead of s, you have like s minus 5. Then that means when you reverse the transform, just ignore the minus 5 to find the original function, but also multiply by e to the negative 5t, or e to the 5t, I guess. So there are certain modifications you can apply that behave in predictable ways. Anytime you multiply a function of t by an exponential function, that just has the effect of shifting the Laplace transform, shifting the function of s by that number of spaces. And likewise, multiplying the function of t times t has the effect of taking the negative derivative of the function of s. And there are other predictable things also as well, and other modifications you can make to one function that cause a predictable corresponding change in the other function. And those are all listed in the Laplace transform table in the textbook also in section 6.2. Any other questions on that so far?
No, thank you.
Anything else you want to work on? Or any other questions in general?
I don't think I have any right now.
All right. Well, feel free to let me know if you have any other questions, and I will see you next time.
Thank you.
You're welcome.